it's always a great feeling to come back to JNU, where I spent considerable amount of time. And I thank Satyabrata Patnaik for making that possible. As it turns out, the previous lecture has some overlap with mine, so that it may be easier for you to follow. For instance, things like spin-orbit coupling, Hall effect, what happens under electric field, the transport properties, they've all been mentioned here. So I will try to explain to you various terms that appear in the title itself. Right. So what is the Rashba effect? This is just for the students. Rashba effect is nothing but a spin-orbit interaction. So what is spin-orbit interaction? As you all have learned from, let's say, Jackson's book in your MSc days, in electromagnetic theory, when electromagnetic theory is combined with Maxwell's equations and special theory of relativity, that if I have a simple atom, like hydrogen atom, I have a nucleus at the center and a single electron moving around it. The nucleus creates a Coulomb field at the site of the electron, so the electric field. So that's in a radial direction. So that's proportional to the vector r. However, the electron, well, this is the so-called Born-Oppenheimer. You take the nucleus to be almost stationary. The electron is moving around with a very rapid speed. And the relativity says that in the frame of the electron, in the moving frame, the electric field of created by the nucleus turns into a magnetic field. And that, as it appears in Jackson's book, is given by E, the electric field vector, cross product with the velocity vector. So that's the magnetic field. However, the electron has an intrinsic spin. So that electronic spin will interact with the magnetic field, so-called Zeeman interaction. So that is like sigma dotted, it's a scalar product of sigma dotted with the B field. However, the B field, as we discussed, is already E cross V. So you play with this sigma dot E cross V term, and essentially E is proportional to the R vector, and so you get a sigma dot R cross velocity, or P, because you multiply by the mass and that you get the momentum vector. So you get the spin orbit coupling, which was shown by the previous speaker, which is like sigma dot L. Now, Emmanuel Rashba showed in various contexts of condensed matter physics how that spin orbit interaction can be manifested. So as a tribute to Rashba, some 4 years ago, in 1922, the December PhysRev B issue was dedicated to him on his 95th birthday. And so the Physical Review wanted to have a few more papers on the Rashba effect, and Bert Halperin was there. So I submitted a paper there. So that's the first reference. So this is PhysRev B in 2023. And my work was based on the experimental work done on AMR, which is anisotropic magnetoresistance, and PHE is planar Hall effect. So I'm just explaining various terms that appear here. And already in the morning, Odindam Ghosh talked about the last 2 decades of great excitement in 2D materials. So this is also a 2D material, but it's an oxide material layer, one oxide material layer on another. And some familiar people have worked on that. So basically it was driven by the experimental group of Shubhankar Chakravarti, who is in the Nanoscience Institute in Chandigarh. He's not there in this meeting, but Shubhankar was there with us at the S.N. Bose Center when I was there. And he also postdoced with Didi Sharma. So Didi is here. And Jogesh Singh is also here in the conference. I don't see him in the audience, though. So there were some experimental papers earlier, but I would like to focus on a paper written by Shubhankar and company. Jogesh is also there. And the theoretical work was done by Sanjeev Kumar at IISER Mohali. And this paper was published in Advanced Quantum Technology. And so the system that they worked on is an interface of lanthanum vanadium oxide and potassium tantalum oxide, abbreviated as LTO-KTO. So what happens is, by pulse laser deposition, Shubhankar and his students created these oxide layers, and just by the method of preparation of the system, you get an intrinsic electric field. So this electric field is not coming from the nucleus of an atom that I mentioned in the case of a hydrogen atom, let's say. By the way, that fine structure splitting that occurs due to spin-orbit coupling is what we did experiments in our BSc, MSc days, where we see the sodium two lines at 5890 and 5896 angstrom. However, so this is now intrinsically created in the laboratory, where the electric field is normal to the plane of the oxide layer. So it's going like that. And so what the experimentalists at Chandigarh did is to apply also a magnetic field. So this electric field will cause the Rashba effect. I'll come back to that. They also applied externally a magnetic field. Indra Das Gupta already talked about the various symmetry breaking effects that occur due to both the electric field and the magnetic field. So they're all there. And so you can tilt the magnetic field experimentally. So I'm going to only focus, for simplicity of the presentation within 25 minutes, is the work done by Shubhankar and company, where the magnetic field is also in the plane of the oxide layer. So the angle, co-latitude angle theta is 90 degree, but you can rotate the angle phi. And so the physics of the problem is that you have the Rashba effect, you have the effect of the magnetic field, and also, of course, electron transfer in the layer, which we will try to model and map in terms of something that you have all learned in Kittel's book or Zeimann's book on the tight binding model. And so you think of a tight binding Hamiltonian in a 2D layer. On top of that, there is this Rashba coupling, which we will introduce soon. And then in addition, you have the Zeeman interaction between the externally applied magnetic field in the plane with the spin of the electron. Okay? Stop me if you have any question. So, what is the basic Hamiltonian? Now, the basic Hamiltonian is the first term, so what we call the system Hamiltonian, H subscript S. I hope it is readable from the back, did it? Yes. Is H0 plus HR. R suffix stands for Rashba. HZ, this is the Zeeman term. Again, the suffix Z stands for Zeeman. And what is H0? H0 is a tight binding Hamiltonian. So as I said, the motion in the two-dimensional plane is modeled as under a la tight binding approximation, where the tight binding approximation, you assume that the electrons are mostly localized at sites, and occasionally they move from one site to the other by quantum mechanical tunneling. And so you write the basic Hamiltonian as minus delta. If you take h bar equal to 1, then delta is the tunneling frequency. Then I'll define the kx and the ky operators. Kx is in the x direction, ky in the y direction, and they're Hermitian adjoint. And what kx does is to take the electron from one side to the next nearest neighbor side. Okay? And I'm assuming the lattice spacing to be D, which occurs here. And so you have transport in both X and Y directions, and you take the Hermitian adjoint of that, and this is the simplest tight binding Hamiltonian. All right? Okay. The Rashba coupling turns out to be minus, of course, the whole thing has to be Hermitian, but you need an imaginary I minus I outside. D is the lattice spacing, and lambda, capital lambda, is a constant coming from the spin-orbit interaction in the system. So it depends on the system parameters. But this most interesting term is here. Sigma x Vy minus sigma y Vx. Vy and Vx are the two y and x components of the velocity operator in this case. Now this Hamiltonian actually looks very much like the Dirac Hamiltonian that was mentioned by Arindam Ghosh in the morning, which was sigma dot v. Here instead you have a kind of a tensorial coupling. It's not sigma dot v, but it has all the attributes of that kind of a coupling because of what is called spintronic behavior. Because you see, spintronic, tronic comes from electronics. Electronics has to do with the motion of electrons. That has to do with the motion of velocity vectors here. And that couples to the spin. And so it's a spintronic behavior, and that's the spin-orbit coupling. And that has all kinds of interesting effects like that were mentioned by the speaker just before me. So I'll not repeat those things here. So this is your Rashba Hamiltonian. And how do you calculate the velocity operator? The velocity operator from Heisenberg equation of motion is basically the time derivative of the number operator. The number operator nx is summation over nx, and then the projection operator nx ket nx bra. And then so you work out the commutator, and the velocity operator will turn out to be I delta kx minus kx dagger. The simplicity of the tight binding model is that kx and kx dagger actually commute with each other. And the number operator also has interesting commutation relationships with the kx and kx operators. And so they are given here. So kx nx commutator gives you minus kx, and kx dagger commutator with nx gives you kx dagger. Kx and kx dagger commute. And so what the presence of the Rashba Hamiltonian, what it does, it intertwines the x and y motion through the spin-orbit interaction. And then on top of all that, you have the experimentally applied Zeeman coupling, which is, and as I said, will focus only on the planar Hall effect geometry, where the Zeeman coupling is minus b sigma x cosine phi plus sigma y sine phi for planar Hall effect. Now, so what is the experimental situation? The experimental situation is that you have a tight binding Hamiltonian, you have a spin-orbit interaction, and you also have a Zeeman interaction. You allow the system sufficiently long time so that the entire system has come to thermal equilibrium, right? Now, you disturb that system experimentally by applying an electric field because you want to find out transport behavior, Hall effect behavior. In Hall effect, in Hall geometry, you have an electric field and also a magnetic field. In this case, the magnetic field is also in the plane, and the electric field, for simplicity, as is done experimentally, is applied along, let's say, the x direction. So as soon as you apply the electric field, the electrons will be drifted in a certain direction, and so system then goes into a transport mode. It becomes a non-equilibrium system, and so therefore there will be transitions. There will be transitions between the eigenstates of your unperturbed system Hamiltonian and the external bath. Because after all, transport, remember the simple transport problem that you must have learned in solid-state physics, the Drude transport, when you switch on a battery and a small electric field, and you look at the response to the velocity vector, and you look at the asymptotic behavior of the velocity vector, and you find out a relationship that the electrical conductivity, which you calculate from the current density J equal to sigma times the electric field. And then the current density is the mean value of the velocity vector that you solve in the asymptotic limit. But you put in a term there, which is a dissipative term, which breaks time reversal symmetry of the equation of motion of the Newtonian type, which comes and which is called the spin lattice, is called the relaxation time or Drude relaxation time. And the net result is that you get in the asymptotic limit a conductivity which is sigma given by ne squared tau over the effective mass of the electron. So the transport problem is essentially a non-equilibrium problem, though you're looking at the asymptotic t equal to infinity limit. So that's what we are trying to calculate. What we are trying to calculate is to find out what is the response to the applied electric field in linear response theory, and that is the Kubo response, where you try to calculate the response to linear order in the electric field in the asymptotic time limit. So let me now, I've given the interactions in a very slow manner. So now you try to find out. It is easy to actually diagonalize the system Hamiltonian because all that happens is that, you see, in the K space is very simple. You have a tight binding model. But the presence of the magnetic field and also the spintronic effect actually makes it a two-state system. You have two different bands, an upper band and a lower band, and you can calculate the matrix elements of the Hamiltonian in the plus-plus state and in the plus-minus state, and they're given here. So therefore, you have two valleys we talked about in the last talk, and you calculate the velocity vector, which is now not the velocity operator that I was talking about earlier. It's like the group velocity or the band velocity. And the band velocity are given by the derivative of the energy eigenvalues with respect to k. So propagation now will occur in two different bands because of the two Zeeman split levels. And here is the Kubo linear response formula. The simplest formula is, as I said, from Kittel's book, you'll have E squared tau, ne squared tau over m. But where is the n coming from? Now you look at more detail, and there's a kBT factor, the Boltzmann temperature energy. So the way it comes about is that if you think of the sigma, the Kubo formula depends on a correlation function of the velocity. Now the velocity of the two band velocities in the two different directions, plus and minus states. And if you now assume in a very simple manner that the velocity correlation dies out exponentially in time with relaxation time equal to tau, then an integral over the velocity correlation over 0 to infinity will give you just simply the tau factor. And if you take the kBT inside, and you remember the velocity correlation is a trace of the rho. Rho is a density operator which has the Gibbsian structure of exponential minus beta e. So the beta, which is 1 over kBT, if you take the beta inside the trace, beta is nothing but the negative derivative of the density operator with respect to the energy. And that's what people use normally in a Boltzmann kinetic theory approach to calculate this conductivity tensor sigma mu nu. But now, and the F function, the density operator now is actually the Fermi distribution function, because you're working with electrons, and here's the Fermi energy. However, what we would like to do is to put the whole system in an open system approach where you have your system Hamiltonian and you want to have a more detailed understanding of where this tau come from. Where does this tau come from? So the generalized Kubo formula is essentially, now you have no tau here, but basically the time correlation function for the velocity vector is given in terms of a propagator, which is an average over an external heat bath. And so the focus is on the time, the relaxation time tau. So the point that I was trying to make was that the band velocities v mu and v nu, etc., have already been calculated from the derivative of the energy eigenvalues with respect to the energy, the k vector. And for anisotropic magnetoresistance, you need rho xx, which is given here. And for planar Hall effect, you need this. And so we like to focus on that. So what are the questions? What is the microscopic picture of tau? Does tau really depend on k and k prime? Dependence of tau on bath parameters and comparison with experiments. So so the open quantum system approach is something, it's a theoretical approach, has come into being in quantum non-equilibrium statistical mechanics, where in general you have a full system which is Hermitian. The entire evolution is unitary. You have a subsystem Hamiltonian, you have a bath Hamiltonian and an interaction term HY, and HY does not commute with either HS or HB, and because of that, if you focus only on the subsystem, that remains in non-equilibrium. How does the treatment get simplified? For LTO, KTO system that Shubhankar and company studied, they went down to around 10 degree Kelvin. They applied a B field of 13 Tesla, and it turns out that the Rashba coupling and the Zeeman coupling are of the same order, around 10 degree Kelvin, while the band Hamiltonian with a tunneling frequency is around 5,000 Kelvin, 500 times these interaction terms, and delta is of the same order as the Fermi energy. Hence, for the calculating the band velocities, you of course need the Zeeman Hamiltonian and the Rashba Hamiltonian, but for calculating the relaxation time, it's a great simplification that you actually don't need to worry about them. And so for calculating this time evolution operator average, you can, in fact, decouple the system and work on an effective one-dimensional tight binding model. So since my time is limited, let me just quickly go through. So now you have a one-dimensional tight binding Hamiltonian where only kx, and the energy is the familiar minus 2 delta cosine dkx term. And now what is the interaction term? So as is the practice in open quantum system approach, or either Leggett and company or Ford et al., etc., that the bath is taken to be a bunch of quantum harmonic oscillators, which you write in second quantized notation. And so you have this last term is a bath Hamiltonian, and then you need a coupling term which will induce this relaxation behavior. And the coupling here now, unlike the spin boson Hamiltonian that you may be familiar with, and now you have the NX operator there. Okay, so for this you have to read the paper that I cited, this 2023 Phys B paper. You use a usual, what is called a polaronic transformation. It comes from Holstein's work on polarons, and then you basically write a master equation approach. Again, one of my former colleagues in SPS in JNU, who is no more, was involved in this, but basically it is Sudarshan, and it's called the Gorini, Kosakowski, Sudarshan, Lindblad kind of master equation. These are names that may be familiar with people here. And now I make a small digression. This work for 1D electrical conductivity, as it turns out that if you can make a further conceptual jump where from Einstein's idea of how you relate the electrical conductivity to diffusivity, the diffusivity turns out to be actually the 0 to infinity integral of the velocity correlation function, but the diffusivity from Brownian motion idea, is the ddt of mean square displacement, and that's what you calculate. Okay? Now, I don't want you to go through the details. Basically, you need a structure for the external bath. And so for the spectral density, you can assume the much used ohmic model. And then this is the final result for the relaxation time or the Kubo time, the Drude-Kubo generalized time. Then we calculated for the planar Hall resistance the rho XX term, and then plotted it along the phi direction, and those match very well with the experimental results of Shavankar and company at INST. And the difference, however, from their earlier work based on the Boltzmann kinetic equation is that here you have a microscopic analysis of the Kubo time that occurs in that formula, and the Kubo time is given in terms of various Bath parameters, the Bath cutoff frequency omega c for the ohmic form of the dissipation of the spectral function, and a parameter alpha, and the temperature goes in there. And so we also plot, this is something that they have not yet measured experimentally, that how does that time change with temperature. I'm so sorry that though I gave those two figures separately to Professor Patnaik, somehow they have not been loaded. So I think I should stop here, and I'll be very happy to take questions.
Thank you so much. So the session is now open for questions.
You showed Kubo linear response theory. Do you have any prescription how to calculate it? Because those are computationally very expensive to my understanding.
Yeah, sure. We'll be in touch.
Yeah, sure. Yeah. Because it's not very easy to compute the expression that you showed. Computationally it's almost next to impossible for a realistic.
In this case, we can do. We can carry through everything analytically.
I see.
Because of the experimental situation of the energy scale separations. If you did not have that, if the band Hamiltonian and the tunneling frequency was comparable to the Rashba term and the Zeeman term, then it's much more complicated. You may have to do things numerically.
That's why I'm asking. Otherwise,
that approximation, whatever the.
But that is I belong to a generation where we like to work with experimentalists. Experimentally, whatever has been seen is there in the theory. If they find out more things experimentally, we'll delve more into the theory.
And is it very specific to this kind of LAO KTO structure, or?
The open quantum system approach is very general.
Yeah.
It's a general approach to non-equilibrium quantum statistical mechanics, and it has many applications in quantum tunneling, with Leggett and the last 20 years, and also quantum Langevin equations of Swansea and others. To apply this to this specific system for planar Hall effect has, however, that application has been made in a simplified manner because of the experimental situation.
Thank you so much. If there is no other question, let us thank the speaker for his talk.